we're going to begin by talking about descriptive statistics. Descriptive statistics, as the name suggests, simply describe what you have. They take the data that you have in hand, and all we're doing is organizing it in a way that's easier to deal with, easier to work with, easier to, frankly, remember. Descriptive statistics are as simple as, suppose I have a large class, and I give everyone in the class a test. And now I want to see how everyone in the class did on the test. Well, as I go from person to person, and each person reports to me their test score, holding on to all those test scores, remembering all those test scores, is going to be very, very difficult. It's going to be like holding on to so many loose marbles. And when I'm trying to hold on to a bunch of loose marbles, I don't just try to hold them in my hand. If I'm smart, what I try to do is get a container, a little satchel, a box to hold the marbles in. Well, the first thing statistics does for you is it gives you this container for your marbles. Instead of having to hold on to all the individual scores, I can organize them in a way that's easy to hold on to. I can put them in a container, and the container is called a distribution. If epidemiology is understanding the world in terms of ratios, statistics is understanding the world in terms of distributions. Understanding the world in terms of the simple organized form we call a distribution. Once I have the data organized in this distribution form, I can then hold on to the key ideas about the data, hold on to the distribution by remembering not everybody's individual score, but just two simple numbers. One, some measure of central tendency, where along a dimension high versus low this distribution is, and then two, some measure of variation or spread, which is a fancy way of saying how fat or thin is the distribution that we're looking at. With just these two numbers, two parameters, central tendency and variation, I can hold on to a stunning amount of data by the simple summary provided by the distribution. Now, whether you like statistics or not, you have to admit to me, that's much easier than trying to deal with and remember everybody's individual score. The way I'd like you to think about this is, well, when you read the research literature, at the start of every article, there's an abstract. 100, 150 word abstract that summarizes the essentials of what's in the article. Mostly, as we read the literature, we read the abstract. Unless we're very interested, we don't go on to read all the detail of the article. And that's okay. That's what the abstract's there for, to make sure you can go through a lot of literature relatively quickly. Well, what statistics is doing for you here, descriptive statistics, is providing you an abstract of the data. By central tendency, by variation, we're getting an important summary of the essentials of the information. Now we lose some detail, the way an abstract leaves out some of the detail of the article, but we get to hold on to the essentials and therefore have a very good, useful, utilitarian sense of the information provided. We hold the essentials, but we lose some detail. This becomes a very, very useful tool. It lets us deal with a lot of complicated things by this simplifying idea of putting them into a distribution. Now, I flash up here a simple picture of a normal curve, bell-shaped curve, Gaussian distribution, whatever term you prefer. I do this to remind you that a stunning amount of the world, empirically, turns out to be normally distributed. Now, I remind you, a normal distribution is, well, the lower frequencies are on the tail, the highest frequencies in the middle, as you see before you, and also these normal distributions are symmetric. If you cut it right in the middle where that line is, fold the two halves over, they should match exactly. Normal distribution, small frequency in the tail, highest frequency in the middle, and they're absolutely symmetrical. And once I know I have a normal distribution, and once I know what central tendency is and some measure of variation, once again, I get to hold on a stunning amount of information by those two or three very simple numbers and ideas. So let's turn our attention to understanding these two parameters. First, central tendency, and then with that in place, we'll turn our attention to variation. There's three ways that we measure central tendency. Most of you are familiar with these already. Mean, median, and mode, sometimes called the 3M Corporation. The mean is the arithmetic average. Take all the scores, add them together, divide by the number of scores, and you have the mean. That's fairly straightforward. The median. The median is the midpoint. If you take all the values of the data, rank order them, the number in the middle, 50% above, 50% below, is the median. If you have an even number of values where there's 2 in the middle, well, then we derive the median by a simple convention. That's all it is. We take the middle 2 numbers, add them together, divide by 2, and that becomes what we use as a median. Again, it's mere convention. There's no other reason for doing it that way. The mode. The mode is simply the most common value. What do you have the most of? The highest frequency. On a graph, it's going to be the high point on the graph. Mean, median, and mode, the 3 ways to represent central tendency, and you're in luck, because in a normal distribution, they're all the same value. That is, if you know the distribution is normal, and you know the mean, you also know the median and the mode. Let's say I give the class a test, and let's say I tell you the most common score on that test was 73%. And now I ask you, what's the mean for the class? Well, that's easy. I just told you the mode was 73. If we assume a normal distribution, very likely for an exam, then you know the mean is also 73. And a normal distribution, if you know 1 for central tendency, you know them all. But not everything in the world is a normal distribution. Some distributions can be a little off-center. Some distributions can be what we call skewed. You see before you now representations of a positively skewed distribution and a negatively skewed distribution. Let's look at the names here. Positively skewed is on the right because the tail, like a finger pointing, is pointing in the positive direction. Negatively skewed is on the left because the tail, like a finger pointing, is pointing in the negative direction. In this culture, positive to the right, negative to the left. Notice the curves are defined not by the hump, but by the pointing of the tail. On the right, positively skewed, pointing to the right. On the left, negatively skewed, pointing to the left. Now, focus on the positively skewed distribution to the right with me. In that positively skewed distribution, I've drawn 3 lines which I've labeled with the letters A, B, and C. These letters represent the 3 kinds of central tendency: mean, median, and mode. Which is which? Well, which is the mean? The mean turns out to be C. Which is the median? The median turns out to be B. Which is the mode? The mode would therefore, the one remaining, be A. How can I say that with such conviction? Easy. Because in any skewed distribution, it's always going to be in that order. You go to the tail, you count in, and you first encounter the mean, and then the median, and then the mode. See, the mean is more sensitive to, pulled upward by, in this case, extreme values. The median less so, and the mode not at all. So counting in from the tail, you're first encountering the mean, and then the median, and then the mode. Now, by the way, if you get confused about the order, here's a hint. Do you notice? It's alphabetical. MEA, MED, MOD. First mean, then median, then mode. Predictable, and always going to be that way in a positively skewed distribution. Now, I want to make sure you're following this general concept, and so let's take a moment and flip our attention over to the negatively skewed distribution. The negatively skewed distribution again has 3 lines. This time I'll label them with numbers 1, 2, and 3. Which is the mean? Which is the median? Which is the mode? Well, the mean is 1. The median is 2. The mode is 3. And again, how can I say that with such conviction? Because once again, it's always going to be in that order. Counting in from the tail, that's the place to start. You'll first encounter the mean, and then the median, and then the mode. Notice the values for these are not based on the height of the curve. We're talking about values along the horizontal number line. The height of the curve is simply telling you the frequency at each given value here. Counting it from the tail, you first encounter the mean, and then the median, and then the mode. Now, look what else I've just given you. I've just handed you a simple index for telling me whether a distribution is positively skewed, negatively skewed, or normal without ever looking at a graphic presentation. How? Easy. Compare the mean to the median. If the mean is a greater number than the median, it must be a positive skew, right? If the mean is a lower number than the median, it must be a negative skew, right? If the mean and median are exactly the same value, then it's likely, not necessarily, but likely, a normal distribution. And this is, in fact, how we calculate skewness. It's a calculation that compares the mean to the median. The mean is larger, positive skew. The mean is less, negative skew. The mean and median are the same value. It's likely a normal distribution. And that's central tendency. Fairly straightforward, easy indices, as they're intended to be, as a way to just quickly summarize a key factor of the distribution that you're looking at. Let's now leave behind central tendency and turn our attention to the second parameter to describe our distribution. I want to talk about variation. I want to talk here about how we're going to represent variation is a fancy way for saying how fat or thin is the distribution that we're looking at. Well, there's a number of indices that have been proposed over the years to represent the variation in the distribution. And one of the most easy to recognize, easy to compute, is the range. The range is simply the difference between the highest and the lowest score in the distribution. Again, it's easy to compute. It's intuitively obvious what it means. The range is something people usually understand before it's really explained in great detail. But I'm going to try to suggest to you the range is a pretty poor measure of variation. In general, we don't use it. I'm going to try to give you some reasons why we don't use it. First, the range focuses on only two values out of the entire distribution. When we're using the range, we're just looking at the top and the bottom value out of the distribution. All the other available information is simply ignored, and that's not right on some level. Second, you probably know if I give you a test today, let's say, and then I give you a similar test next week, your score is likely to shift somewhat between today and next week, right? What you may not know is certain scores are likely to shift, that is, change over time more than others. The scores that are most likely to shift are the most extreme scores in the distribution, that is, the very highest and the very lowest, and they're likely to shift in a predictable direction, that is, to be down closer towards the mean. We call this phenomenon regression towards the mean. And all regression towards the mean is telling us is, here we go, that extreme values, once they're reassessed, are likely to measure less extreme the next time. I'll say that again. Extreme values, when they're reassessed, are likely to measure less extreme the next time. Now stop and think with me for a moment. You see why the range is a pretty poor indicator? First, we're using only two values, ignoring all the other available information. And secondly, in a very fundamental sense, we're using the worst two possible values. We're using the least stable values. To use vocabulary from epidemiology, the least reliable of all the data we have. That means the range is highly changeable. It's not something that is constant. It's therefore not a very good indicator. Don't use the range. Before I go on and talk about what we do use, I just want to linger here a little bit longer with you and just get you a little bit more familiar with this idea of regression towards the mean. Here's the concept again. Extreme values, when reassessed, are likely to measure less extreme the next time. Now again, that's not guaranteed. It's just the probability. It's the tendency that they're more likely to come closer towards the center than they are to go more towards the extremity. What's the implications of this kind of idea? Well, let's say we have a student who took their Step 1 USMLE exam and got a very high score. Let's say something really stunningly high, 280, a really good score. And now the same student is going to go out and take their Step 2 CK exam. What's your best guess about what this student's going to do in Step 2 CK? Would you guess they're going to do better than 280, about 280, or worse than 280? Well, if you're following me, the clear way to bet is worse than 280. Because extreme values when reassessed are likely to be less extreme the next time. A really high score is likely to be lower. Now understand, I did not say the student in some sense got dumber between Step 1 and Step 2 CK. What I said is the measurement will be lower. And here's the key issue. Once again, we're back to that old canard, numbers are not reality. See, it's not that the reality changed, it's the perception of reality changed because of the vagaries of what measurement is. Remember, every measurement is reality plus error. And if the error in my measurement, in one instance, takes me to the extreme, the next time I measure, the error is likely to be simply less extreme. And that less extremity is likely to give me a score down closer towards the mean. Again, you're going to find exceptions to this rule, but the way to bet, the highest probability, is extreme values are likely to be less extreme. What might this mean in a clinical situation? All right, let's suppose you have a patient comes in to see you, standard physical exam. In the course of working up this patient, you discover they have the highest blood pressure you have ever seen in an ambulatory human being. Concerned, you leap into action. You prescribe dietary change, strong medication, exercise regimen, and you're so concerned about what you've seen that you want to see the patient back in your office 2 days later just to double check and see how things are going. 2 days later, the patient comes back to your office. Again, blood pressure is assessed. And the second time, says the question, the blood pressure measures substantially lower than it did on the first encounter. To what should the physician attribute this lower blood pressure measurement on the second visit? What do you think? Drug? Diet? Exercise? No, none of that. It's regression towards the mean. Extreme values reassessed are likely to be less extreme the next time. Understand, I didn't say the patient's blood pressure actually changed. It probably didn't. It's just the perception of changes there because of the issues regarding measurement. Well, because of this regression towards the mean phenomenon, and because range only focuses on 2 values, excluding everything else, the range is a really poor measure of variation. In general, don't use it. What should we use instead? Well, statisticians sat down and tried to think of a solution to this problem, came up with what I think anyhow is a pretty ingenious solution. They said, hey, let's start with what we have. Let's start with each score, x, and let's subtract x bar, the mean, from every score. We have written here x minus x bar, which is taking each score and subtracting the mean from it. If we have in the distribution 50 different scores, we're going to do 50 different subtractions. And then the sigma is, of course, the summation sign. We're then going to add together all these 50 resulting subtractions. Okay, now stop for a second. This is a pretty intuitively useful index, is it not? Because we're going to take the mean as a central pivot point, and then we're going to, by subtraction, seeing how far every single score is above and below the mean, and then we're going to sum all those together to get an index about the spread of the scores around the mean. Very clever, is it not? Well, at least theoretically, this is clever. Practically, this index doesn't work. Practically, this index buys you nothing. Why? Because if you do this calculation, whatever data you want to start with, you can pick whatever data you want, you're always going to get the exact same answer. What answer you're going to get? Come on, think about this. The answer you're going to get is, right, 0. You're always going to get 0 for your answer, because for every positive number, there will be a negative number. The positives and negatives will cancel each other out, and so you end up back at 0. Boy, when statisticians first discovered this, they felt really stupid. Now, I don't know how many statisticians you've gotten to know in your time, but let me tell you something about them. Statisticians, in my experience, above all, they do not like to appear stupid. They like to look smart in all things. And so whatever statisticians think they might look stupid, they have a number of gimmicks that they use to make themselves look intelligent. One of the most convincing is they square things. Now they look smart. Now they don't just look like run-of-the-mill people, but once you put that square there, it looks like you're onto something really, really important. Come on. E equals MC. That doesn't sound nearly as profound as E equals MC squared, right? Isn't it the square that sells it? Sure, and not only does it make them look smart, it solves the problem here. Because now, instead of summing together pluses and minuses, which cancel out, by squaring the number, we have nothing but positive numbers. We're now adding together simply summation of only positive numbers, getting a larger and larger number as the addition progresses. But we have a couple of small things we have to solve here before this index is truly useful. Here's one problem. Suppose you have somebody doing research and they have a sample of maybe 100 people and they compute this index. You have somebody else doing research, they have a sample of maybe 1,000 people, they compute this index. Well, the person with 1,000 people is going to get a much larger number here, right? Because they're summing together 1,000 squared differences compared to the person summing together only 100 squared differences. So this number is going to rise or fall dramatically with sample size, right? Well, we can't have that. Would be nice to have an index that's fairly stable across sample size. And so to make this work, we're going to take this and now divide it by the sample size. Divide by n. Now, I've written n minus 1 here because that's the correct formula. And I'm now just going to take a brief moment and explain to you what that minus 1 means. That minus 1 is called a degree of freedom. Degree of freedom, well, the sample size is simply telling you the amount of information you have to work with. As the sample size increases, the information you have to work with increases. The problem is, when you computed the mean here, as you've done in this formula, you've already used some information, have you not? You've used what we say is at least 1 degree of freedom. So the minus 1 is basic honesty. confessing that we know we've already used some of our information. Now, if the sample size is large, close to infinity, that -1 is trivial. Literally, you can forget all about it. But if the sample size is relatively small, under 20, that -1 actually changes the answer. Now, I don't need you to agonize about it. I've just talked about the degree of freedom so you understand what that means when you hear it. All I really need to remember here is we're dividing by the sample size. So we're going to have a relatively constant value even when sample size changes. Okay, we're almost home. We have one more thing to finish here. Right now we have squared units. If I was measuring something in feet, I now have squared feet. Well, I don't want to have a squared unit. I want to get back to the original units I started with, don't you think? To do that, well, if I have a square, how do I get back to the original units I started with? That's easy. I take the square root of the whole thing. And when I take the square root of the whole thing, I've now given you the formula for S, which is the standard deviation. Say that again. S, when you see it, represents the standard deviation. Just as an aside, if you ever see the term the variance, well, the variance is simply S squared. In short, if you don't take the square root of this quantity, you're left with the variance. The variance gets used in a lot of statistical calculations. For your purposes, it's unlikely to be useful. Instead, I want you to focus on the standard deviation. Now, why did I just build for you the formula for the standard deviation from scratch? First, some comfort. You will not be asked to compute this value on the Step 1 exam. How can I say that with such clarity? I can't do one of these without a calculator in 2 minutes. You can't either. So don't expect to have to do the calculation. Why did I build you the formula? 2 reasons, really. 1, so the standard deviation isn't a mystery. This is not some magical quantity given down from the deities. This is simply taking the data, creating an index in a way that makes mathematical sense, looking at the spread of the data around that central tendency and summing it together to get a useful index. A larger standard deviation means, of course, a fatter distribution. A smaller standard deviation means, of course, a thinner distribution. And second, I give you the formula so you can answer simple questions for me. Simple questions such as true or false. As the sample size increases, the standard deviation then tends to increase, right? Well, of course not. As we just said, the standard deviation tends to be stunningly constant across changes in sample size. You know the way the mean is fairly constant even with changes in sample size? The standard deviation is fairly constant with changes in sample size. In fact, that's a good way to think about the standard deviation. The standard deviation is basically the average deviation. It's the average deviation the way the mean is the average for central tendency. It's not the calculation of the standard deviation that you're going to need. It's the application of the standard deviation, which you're going to see as you turn to focus on this particular graph. Now, this graph that you see before you, I'm hoping, is essentially an old friend. I'm hoping this is something you've seen before in your education. I'm hoping this is going to be simply mild review. If that's not the case, now's the time to make it your friend. We're looking here together at a set of constants. These numbers we're presenting are always true in every normal distribution. Whatever the computed mean or standard deviation, these percentages relative to the standard deviation units in the curve are always going to be true. And so it's crucial that you know these. Frankly, every physician should know these, flashcard ready. Not so you sit there, draw them out, reason it out. These should be numbers you have, they're available. You can do mental calculations using them without being given any additional information. There's 2 sets of numbers in the graph before you. First, the numbers on top, the so-called symmetric numbers. Use the mean as a pivot point going equidistant above and below the mean. And then secondly, the more important numbers, I believe, the numbers on the bottom, the so-called asymmetric numbers, describing discrete areas bounded by standard deviation units in, again, every normal distribution. Let's walk through these numbers, trying to help you put down a memory trace, and then after our review, we'll go through and do some problems based on this particular graph. So, let me ask you, so you can talk back to me about this. In every normal distribution, what percent of the cases fall within plus or minus 1 standard deviation? Well, as the graph tells you, 68%. 68% plus or minus 1 standard deviation, same amount up as down. What percent of the cases fall within 2 standard deviations and normal distribution? That answer is 95.5. Please note, not just 95, but 95.5. We're smidge over that 95. In any normal distribution, what percent of the cases fall within plus or minus 3 standard deviations? That turns out to be 99.7. Please notice, you don't get to 100%, but we're even over 99%. So for practical purposes, plus or minus 3 standard deviations gives you just about everybody you'd ever care about in any given distribution. The numbers again, plus or minus 1, 68, plus or minus 2, 95.5, plus or minus 3, 99.7% of the cases. Okay. With those, let's keep those in our heads. But now let's move on to talk about the asymmetric numbers, the numbers down at the bottom part of the chart. Here we're talking about the area, that is the percentage of cases in the bounded areas described by standard deviation units. Let us do this again by question and answer. In any normal distribution, what percent of the cases fall between the mean and 1 standard deviation above the mean? Well, that's easy, 34%. Why is that easy? Well, because it's a symmetrical distribution. If plus or minus 1 standard deviation is 68, it has to be half of that on each side of the mean, therefore 34%. In any normal distribution, what percent of the cases fall between 1 standard deviation above the mean and 2 above the mean? That's easy, 13.5%. In any normal distribution, what percent of the cases fall between 2 standard deviations above the mean and 3 above the mean? That's easy as well, 2.4%. And what percent of the cases in any normal distribution fall above 3 standard deviations above the mean? That's easy, 0.15%. Please note, less than 1%. Now, taken all together, all those numbers of the red box at the bottom here should sum to 100%, but they do not. And why? Basically, we've given you easier to use numbers than the actual numbers. We've given you rounded numbers, and we've lost about 1% in the rounding. None of these numbers presented on the slide, you should be aware, are as simple as they appear. All of these, to be absolutely pristine, should go out to 6, sometimes 12 different decimal places. But you don't really need to do that for day-to-day utilitarian usage, and you certainly don't need to do that in order to answer questions on the exam. So these are the utilitarian numbers that you should know for your exam. And I remind you again, you should have these numbers flashcard ready. Not so you take out your whiteboard, you draw the distribution and label it. You ought to have these numbers in your head, you can use them, and they're available to you to do your reasoning exercises. What kind of questions might you need to answer using these numbers? Let's do a few examples together to give you an idea here. First, in any normal curve, what percent of the cases are below 2 standard deviations below the mean? Below 2 standard deviations below the mean. Now notice there's 2 things here. One is where you're starting, and the second one is which direction you go. This is below 2 standard deviations below the mean. So where am I starting? Here, 2 standard deviations below the mean, minus 2s. And which direction am I going? Below that, that means this way, from that point all the way down. What percent of the cases are there? Rounded off, it's roughly 2.5%. There's certain means and standard deviations we expect you to know as you walk into the exam. For example, we expect you to know the mean and the standard deviation of the IQ distribution. What's the mean of the IQ distribution? Well, in case you forgot, it's 100. IQ is always constructed out of a mean of 100. What's the standard deviation of the IQ distribution? 15. Mean of 100, standard deviation of 15. So, what percent of the U.S. population has an IQ below 70? What percent of the U.S. population has an IQ below 70? Let's think this through. The mean is 100. So I go to the mean, x bar, and that's 100. I drop down 1 standard deviation, I'm now at minus 1s, that's minus 15 points, that would be 85. I drop down another standard deviation, I'm now minus 2s, and that's going to be 70. What percent of the U.S. population is an IQ below 70? 2.5%. Why is 70 the cutoff for mental retardation? Because it is 2 standard deviations below the mean. Remember, what percent of the U.S. population is mentally retarded? That's fairly easy. Since 70 is the cutoff for mental retardation, 2.5% of the population is mentally retarded. These numbers are constant, they're useful, they're all over medicine and all over day-to-day life. When you get your lab values and we give you a reference range, what is that? It's the mean plus or minus 2 standard deviations, trying to tell you that These are the values that are, quote, normal, that is expected, and anything beyond that is abnormal, that is unexpected. Notice lab values outside the reference range don't mean pathology, they mean abnormal, which is your job to then figure out why we're getting these abnormalities. Next, in any normal curve, what percent of the cases are above 1 standard deviation below the mean? Above 1 standard deviation below the mean. Once again, we have two things here. One is where to start, the second is where to go. So, in this case, I'm going to start where? 1 standard deviation below the mean. And then I'm going to which direction? It says above that. And so from that point, 1 standard deviation below the mean, all the way up to the top, that's going to be 84%. Now, I can get that 84% relatively quickly, can I not? Because it's going to be 34, 1 standard deviation below the mean until the mean, plus 50. Why plus 50? Because the mean is also the median. So any of you that were sitting there adding together all those little individual percentages, yeah, stop that now. Let's do it the easy way. It's that 34 plus 50, and you have your 84. Oh, by the way, and what percentage of the cases are below that specified point? Minus 1s? Well, that's easy. That has to be 16%. The whole thing's 100. If it's 84 above, it must be 16 below. And please notice once again, this is purely a logic exercise. Once you have the numbers, it's just a matter of reasoning, thinking clearly in order to answer the questions that are presented. Next, we have a student who scores at the 97.5 percentile. 97.5 percentile. Where's this student on the curve? Well, let's look back at our graph once again. You know that the mean would be the 50th percentile. From the mean downward are 50% of the cases, right? So as I go up 1 standard deviation, I now gain another 34%. 50 plus 34, 1 standard deviation above the mean is the 84th percentile. As I go up a 2nd standard deviation to the 84, I now add 13.5. So 2 standard deviations is now the 97.5 percentile. From that point downward, I've beaten 97.5% of all the students. From that point upward, we have a remainder of course, 2.5%, everything being 100. This is what we mean by percentile, by the way. It's simply what percentage of the students did you beat. And so, just to do this as a way of talking you through the concept, at negative 2s, 2 standard deviations below the mean, we're at the 2.5 percentile roughly. When we're at minus 1s, we're at the 16th percentile. When we're at the mean, we're at the 50th percentile. When we're plus 1s, we're at the 84th percentile. When we're plus 2s, we're at the 97.5 percentile. Next, let's look at something a little bit different. A student took 2 tests. On which of the tests did the student do better relative to his classmates? We have test A, where the student scored 45%, and we have test B, where the student scored 60%. The question is, which is better? And the answer is, right now, given what's on the screen before you, you can't tell. Because scores by themselves are essentially meaningless. Scores only have meaning when they're linked to the distribution out of which they came. We need information about the distribution to get a sense of the true value of the scores. All right, so let's give you some information about the distribution. The mean for test A is 30%. The mean for test B is 40%. Which one of these 2 scores, 45 or 60, is better? Again, you can't tell yet, because we represent distributions not merely by central tendency, but by central tendency combined with the second parameter, some measure variation, for which a standard deviation would be a usual representation. All right, let me give you a standard deviation, and now answer the question, which score is better, A or B? The answer is A. 45% is a better score, and here's why. Whichever one of these 2 is more standard deviations above the mean is a better score. It's a higher percentile score, if you want to think about it that way. The way to look at this, simply, mechanically, we're going to go to the mean, we're going to add standard deviation units, and we're going to stop when we hit the student score. Whichever one lets us add in more standard deviation units is simply a, well, better test score. So, I go to 30, I add in 5%, 35, 5% again, 40, 5% a third time, 45%, stop. Test A, the score is 3 standard deviations above the mean. Let's drop down. I go to test B, where I have a mean of 40%. I add 10%, that's 50, 10% again, that's 60. Stop. Test B is 2 standard deviations above the mean. Both are good scores, but test A is simply best. Test B, the student scored 2 standard deviations above the mean, the 97.5 percentile. Test A, the student scored 3 standard deviations above the mean, the 99.85 percentile, with just 0.15% of the population above that particular point. Both are stunningly good scores. You'd be happy with any of these, but the question was, which is better? A is better. Please notice, if the student scored below the mean, then the number that's the fewest standard deviations below the mean would be the best score, because that would be, again, the highest percentile score. And this is descriptive statistics. What we're doing with descriptive statistics is just giving you tools to summarize and describe the data that you have before you. No longer do you have to focus on remembering all the individual values. You can summarize in a distribution and then represent the distribution yourself. And then we try to look at some of the regularities we find in these distributions, especially in the normal distribution, and especially percentages related to standard deviation units. These regularities give us useful tools and let us do useful reasoning exercises.